how about we do some awesome physics problems? So these are curves, and I'm going to use real roads, and we're going to look at, how fast can you go around a different curve. So let's start with the very important idea that we're going to use here. There's a couple ideas, but the most important one is the centripetal acceleration. So I have a video deriving this formula for centripetal acceleration, but the short answer is if you have an object moving in a circle, then at a constant speed, so the magnitude of the velocity is constant, then it will have an acceleration pointed towards the center of the circle. We call that centripetal acceleration, which literally means center, pointing. And it has a value of v squared, the magnitude of the velocity squared, divided by the radius of the circle. I guess I should say this too. We're also going to use Newton's second law, which says the total force, F net, is mass times acceleration. We are also going to have to use the frictional force, the model for frictional force. This has a magnitude, a static friction magnitude is less than or equal to the coefficient of static friction times the normal force. So that gets a little tricky. We're going to be using cases of maximum friction force. We're going to set this equal to it, but that's what we're going to use. So how do you, I guess, let me show you the problem, and then I'll come back to this solution right here. So the question is, I want to know what speed limit I should put for this on-ramp. So let me switch over here to Google Maps. Okay, so this is Google Maps. This is in the area where I live. This is in Louisiana, and I go on this road right here. This is I-55, and this is I-12. So I-12, is a bypass for I-10. But it goes all. So it's two big roads. Let's look at this intersection right here. So you have these on ramps, and these I guess they're off ramps. You've been on these kind of things, and they can be kind of tight turns. So the question is, what speed limit should you put on these ramps? So I like this one right here. This is going from I-55 north to I-12 west. I actually don't take that one. I don't think I've ever taken that one. I probably have, but I usually use the other ones because I usually go this way to Baton Rouge, or that way to Mississippi, or that way to New Orleans. But I never go from New Orleans to Baton Rouge. So, okay, you don't care about that. No one cares. Just give me the physics problem. That's what you're saying. Just give me the physics problem. Okay, let's look at this curve right here, and let's find how fast you should go around that. Now I'm going to make the assumption that it's a flat road, and we can change that later. So the first thing I want to do is I want to actually measure the radius of curve, the radius here. So this is almost a circle, so I'm just going to measure the distance from here. So if you right click in Google Maps, you can say measure a distance. You'll drop a point, and then you click again, and it gives you a distance. Isn't that very nice? So this says this is a diameter of 112 meters. Okay, so now let's go back and draw a picture and solve this problem. I want to know how fast you're going to go around that. Okay, switching back to the other camera, the paper. Okay, so I know that I have, I want to find out how fast. So the first thing I want to do for all these kind of problems is draw a picture. So here's my picture. Here's my ramp. It's kind of a circle, and I'm going to have the car right there. And then this is D, and D equals 112. Let's just say 112 meters. Yep. Okay. And let's say it technically be going this way, V. So the first thing I need to do is to draw a picture. Got that. I also kind of want to do this. V equals, I don't know what I'm looking for. I want to say something like R equals D over 2. You may think in the top of your head, oh, what about the mass? I don't know that. Well, let's just leave it out. What about the coefficient of friction? Okay, I looked that up beforehand. So mu wet for a car is 0.4. Mu dry is 0.7. So the coefficient of static friction between a tire and the road when the road is wet is 0.4, and when it's dry it's 0.07. I looked that up. Okay, so we've got our picture, but we really need to draw a force diagram in order to get this part right here. We may need a little different picture. So suppose I do this. Suppose I have my road. Here's my road. And then here's my car. There's the wheels. there's the, and there's a person inside. So this car is coming out of the paper, is coming this way. And it's nice to draw that because now I can identify all the forces acting on it. So when you start drawing forces, you want to think of two things: contact forces and long-range forces. So what's touching the car and what's a long-range force? In almost every situation, the only long-range force you're going to have is the gravitational force. So I'm going to draw it off to the side. I have the gravitational force pulling down. It has a value of mass times the gravitational field G. I don't know the mass. That's fine. I do know G. The magnitude of G is 9.8 newtons per kilogram. Okay, so I don't have any of the long-range forces. What's touching the car? It's just the road. So the road can actually exert two different forces. It can push up on the car, and it can have a frictional force. So we have the normal force pushing up like this, and then there's a frictional force this way. And so friction, static friction opposes the change in motion. It wants to make two surfaces not slide. So the car would want to keep going in a straight line, and so that would move it off the path. So this wants to push it towards the center of the orbit over here, orbit, turn. So this is a distance of r. So the next thing I want to do is to draw my x and y axis. The key here is that you can pick any x and y axis, but it's going to help a lot if you pick the x-axis or the y-axis, one of those as the direction of your acceleration. That way you only have an acceleration on one axis, the other axis has zero acceleration. So I'm going to pick this as my x and y axis. I'm going to pick x is that way and y is that way. So with that, I can use this equation. So that's my x. I should draw those dotted. X, and this is y. I can write down Newton's second law in the x and the y direction. This is a vector equation, but I can write this as F net x equals max and F net y equals may. So I'm going to write it right here and run out of space, but that's fine. F net x is going to be, so what forces do I have acting in the x direction? It's just this frictional force. That's the only thing, and it's in the negative x direction in this case. So I'm going to write negative F. And that's going to be equal to max. And then I can do the same thing for y. F net, I'm not running, I'm still okay. F net y is going to be equal to n, right? Have the normal force in the y direction. And then mg is in the negative y direction, so it's going to be negative mg. Now, since the car stays on flat ground, the acceleration in the y direction is 0. Okay, so now I have two equations. I don't know the friction force. I don't know the mass. I kind of know the acceleration. I do know the acceleration is going to be v squared over r. And I don't know the normal force. There's a lot of stuff I don't know, but I can still proceed anyway. So let's write those equations. I'm going to put in for the x acceleration. So the F net x equation becomes negative friction. And I'm going to go ahead and say, remember that the friction force is less than or equal to the coefficient of static friction times the normal force. But if I want the speed limit, that means I want to know the maximum speed. The maximum speed would be for the maximum friction. So I'm actually going to use the equal to part, not less than or equal to. So I'm going to say the friction force is just going to be mu times s. So it's negative mu times s, mu s times n, and that's going to equal mass times acceleration, negative v squared over r. It's negative because the acceleration is towards the center of the circle, which is this way, right? So that's why it's in the negative direction. And so, but both of those are negative, so that's cool. Okay, now let's do the y direction, F net. Y, it's going to be n minus mg equals 0. That one's pretty easy. I'm going to go ahead and solve this for n. I'm going to add mg to both sides. N equals mg. Now be very careful. N is equal to mg is a result here, but that's not always the truth. Be very careful. Okay. Now I can plug in that n up here. I can put mg, so I'm going to cancel the negatives because they're on both sides. Mu s mg equals m v squared over r. Check this out. The mass cancels, so that's kind of nice. I'm going to multiply both sides by r, and I get v squared equals mu SGR. Take the square root. V is going to be the square root of mu SGR. Okay, let's calculate this, and then we can convert that to miles per hour just to see what it looks like. Okay, so I'm going to go back over here to the computer. I'm going to switch to Python because I like to use Python as a calculator. You don't have to. And then I forgot to talk about something. Should we use, which mu should we use? So let's just do both. G equals 9.8. That's the magnitude of the gravitational field. Oh, not now. R equals 1/112 over 2. That was my diameter divided by 2. Mu S, let's just call it mu wet, equals 0.4. Mu dry equals 0.7. That's all I need. So now let's calculate V wet and then V dry. V wet is going to be equal to the square root of mu wet times G times R. And then V dry is going to be equal to square root mu dry times G times R. I'm going to go ahead and print those. Let's do this. 1 meter per second in miles per hour. 2.23. So I can use that. 2.24. So let's say print, let's say 2.24. Okay, so print speed limit wet equals V wet meters per second equals V wet times 2.24 miles per hour. Now let's do the same thing for dry. Kind of lazy, so I'm going to copy that, go down here, paste that, and then I'm just going to change this to dry, and this to dry. Maybe you're seeing how awesome Python is for a calculator. Maybe not. That's okay. Yeah, now you definitely see it made an error. Assigning R value. R. Oh. You can't do minus as in your word. That's my own fault. Okay, let's try that. Okay. So I get a speed limit of 33 miles per hour for wet and 44 miles per hour for dry. What do you think the speed limit is? Usually it's like 25, right? And so if you're making a road and you think, okay, wet speed limit, that's the verge, that's the borderline, right? You go any faster than you're flying off the thing. So let's not put it at 33. Let's put a little safety zone in there. So maybe that's where the 25 goes. But I'm pretty happy with that. That seems like a reasonable thing, right? Okay, let's consider now a different problem. What if I had a banked turn? And let's think of a really cool banked turn. I'm thinking of NASCAR speedways. They're in NASCAR, right? Like Talladega is the one that I can come to my mind. So let's look at Talladega Speedway. So Talladega Super Speedway. Okay, there we go. So here's the speedway, Talladega. I already looked it up. These turns are banked at 33 degrees. So if it's banked at 33 degrees, how fast could you go around it and not need friction? That's why they have those banked. So let's switch over here. So here's a curve right there. Okay, so that's pretty circular, and let's assume that's 33. And I don't know if they're all the same. I really don't know a lot about tracks except what I've seen on ESPN. That was from that movie with Tom Cruise. Remember that? Days of Thunder. All I know about NASCAR is what I saw on TV on ESPN. The coverage is quite good. You'd be surprised. That's what he said. Okay, so let's measure. Let's kind of. I could try to measure the diameter, but it's not a complete circle. So I'm going to estimate like down here as the radius of the circle. So let's just measure from here. It's not perfect. It's not perfect. That's fine. So measure distance clear measurement. Measure distance. So that's 227 for the radius. I think that seems kind of reasonable. Let's see if it'll go over here. That's 228. Okay, so let's move this down a little bit. So that's 304. That's 207. So what it should, okay, let's go with 300. 300. Okay, switching back to the paper. New problem. Okay, I'm going to go ahead and draw the same picture that I had, but different. So here's my track. And this is the angle theta of 33 degrees. Theta equals 33. And I'm going to go and say R equals 300 meters. And here's my car. I'm just going to draw this block. And then this is the center of the circle. Okay, so we're going to do the same thing. I want to say how fast V with no friction. No friction needed. Okay. And then we're going to do what's the fastest you could go and what's the slowest you could go. And yes, it might take a little bit of time, but it's going to be fun. And then I'll stop. And then you can go on your day and do whatever you like. Okay, so let's draw the forces on this car. Again, we have the long range force, gravitational force pulling down. I probably should redraw that, but I'm not going to. So let's draw that mg. Then we have the road, and that's it, right? And the road is a normal force this way. It's perpendicular to the road. That's what normal means. And there's no friction. There's no friction. So you've done a problem that looks just like this for a block sliding down a plane, and I get that, okay? And in that case, you put the x-axis this way and the y-axis that way because the block was going to be accelerating in this direction, but it's not accelerating that direction now. And if the car is coming out of the paper, it's accelerating this way. It's accelerating toward the center of the circle. So that's the direction of the acceleration. And I want to put my x-axis that way or the other way. So I want to do this. This is x. And that's y. So if I do that, then I have an acceleration in the y direction of 0 because the car is not moving up or down. If you do an axis this way, you have an acceleration in both the x and the y direction, and you're just asking for trouble, which I respect. You can say, hey, I want to make this hard. I get that. I think that's cool. I respect you. Okay, but I'm going to do it the easy way. So there is one thing. If that's the angle theta, then this is the angle theta, and is this the angle theta? So that's theta. Yeah, that's theta. So what I need is the y component of the normal force and the x component of the normal force. So let's go ahead and write our Newton's second law. I'm sorry, what was I doing? F net x equals. Okay, so what forces are in the x direction? It's a component of the normal force. It's this one up here. So if this is the normal force, the hypotenuse of the triangle, that's the angle theta, then that would be the opposite side. So it's going to be minus n sine theta. Now, notice that I have my acceleration in the negative x direction. That's just the way I drew it. It doesn't really matter. And that's going to be equal to the mass negative m v squared over r. So again, the acceleration is negative v squared over r because it's in the negative x direction. So I went ahead and did that. Now we can do it for the y direction. F net y is going to be equal to, in this case, I have a component of the normal force in the y direction. It's going to be the adjacent side right there. So that's n cosine theta minus mg, and that's equal to 0. Now what do I want to solve for here? I want to solve for v, but I don't know n. So let's use this n right here, solve for n, plug it in up there, and then solve for v. So if I do that, I can add mg to both sides, and I get n cosine theta equals mg. Now I can divide by the cosine of theta. N equals mg divided by the cosine of theta. Now I can plug that in over here. I get rid of the negative signs so they cancel. So I'm going to plug in this, and I get mg over cosine theta. That's my n. I'm going to put in parentheses. Times sine of theta equals mv squared over r. So there's my n. All I did was replace it with that. Again, the mass cancels. It's on both sides. I can multiply both sides by r and take the square root. So v squared is g r sine theta over cosine theta. And you can leave it like that. If you don't do anything, that's cool. But sine over theta, sine over cosine is tangent. So this is actually g r tangent theta. So then I can solve for v. V is the square root of g r tangent theta. I'm going to put that in, but let's just check, right? Because I didn't check the units last time. Let's check the units. So g is 9.8 newtons per kilogram, but it's equivalent to 9.8 meters per second squared. So if I take that and multiply by r is in meters, I get meters squared per second squared. Tangent theta is a ratio, and so it doesn't have units. So this whole thing in here is meters squared per second squared. I take the square root and I get meters per second. So that's good. Okay, so let's plug in and get my value for the velocity, and then we'll get the in miles per hour. And this is the speed it would travel with no friction. I'm going to switch back over here to Trinket Python. I will give you the code for this because I care. So I'm going to use the same thing. And let's just do theta equals 33 times 180, no, times pi divided by 180. So I want the angle in radians because the default function for trig functions in this Python uses radians. And now I can say v no friction equals square root of, oh, I need the new r. So let's say RT for Talladega is 300. The square root of g times r times tangent of theta. Print no friction speed equals v no friction in meters per second equals v no friction times 2.24 miles per hour. Okay, so I get 42. That's really low. Wow. So 42 miles per hour. Does that seem right? I mean, that's pretty. It's Talladega, NASCAR. Should be going faster than that. Just double check. GR10. I think. Okay, let's go with it. Okay, now let's calculate the maximum speed you could go around that turn using the same tires. So in this case, let's assume that it's dry, and let's assume it's the same kind of tires. So back up here, if it's going as fast as possible, then there's going to be a friction force acting on it. And that friction force wants to prevent it from sliding. So you can imagine if it's going too fast, it would go straight, which actually makes it come out of the track. So it would want to go up this thing. So friction is going to be pushing down. So I can add in an extra force right here. I'll call that F. Now you'll notice here, be careful with friction. That's a vector. Because N is not equal to mg. I told you, N is not always equal to mg, and that's the case here. I'm going to have to change my two equations, which I'm going to rewrite. So this friction force has both an x component and a y component. So I need this angle right here is what? That's theta, right? Because this and that are parallel, and that are parallel. So yeah, that's theta. So I can get the x and the y component of this. So let's go ahead and write my new x and y equation, force equation. I'm going to put this right here. Okay. F net x equals what's acting in the x direction? Well, I have the normal force, a component of the normal force, minus n sine of theta, and then I have a component of the frictional force, which is going to be minus ff cosine theta. And that's going to be equal to negative m v squared over r. Now, in the y direction, I have f net y, I have the component of the normal force in cosine theta. Then I have a component of the friction force minus FF sine theta. And then I have the gravitation force minus mg, and that's equal to 0. Okay, so finally, if it's at the fastest speed, then I can say FF magnitude is equal to the coefficient of static friction times n. So I can put that in up here. Let's see. I want to solve, it's not a trivial problem. Let's go ahead and put that in for these two. And let's just rewrite both of them. So friction's in both cases. So I get, then I'm going to multiply this side by negative, both sides. So I get n sine theta plus mu s n cosine theta equals m v squared over r. And this other one is n cosine theta minus mu s n sine theta equals 0. Okay, I guess, this one, the n's cancel. So that one doesn't help at all. Is that? No. I'm sorry, not true. I left off the mg, no wonder. Minus mg equals 0. So let's use this one to solve for n. So I'm gonna add mg to both sides. I'm also gonna factor out the n. So I get n times cosine theta minus mu s times sine theta equals mg. Now I'm going to divide both sides by this. Remember, these are just numbers, so don't get too freaked out over this. N equals mg over cosine theta minus mu s sine theta. Okay, I'm putting a box around that because it's important. Now I can plug that in up here. But before I do that, I'm actually going to factor out the n. So let's just write this as n times sine theta plus mu s cosine theta. So now if I substitute that in, I get, put this in for n, I have, I'm running out of room here, mg over cosine theta minus mu s sine theta, that's n, and then I have that, sine theta plus mu s cosine theta equals m v squared over r. So it looks bad, but I'm really done, right? 'Cause first of all, I can cancel the mass, that's good. Multiply by r and take the square root, and I get v equals the square root of r times g times sine of theta plus mu s cosine theta, all of that over cosine theta minus mu s sine theta. Okay, let's just check. Does it have the right units? Does it make sense? So number one, does it have the right units? I can already see that it does because I have that square root of rg just like before. Sine theta, no units. Mu, no units. Cosine theta, no units. No units, no units. So it's all just meter squared per second squared, square rooted. Units work out fine. Now, what if I take the case where two cases, mu s equals 0, and the case of theta equals 0. If I let theta equal to 0, then I go back to the first problem. The first problem, remember, it was flat, so that would be theta equals 0. If theta is equal to 0, sine of 0 is 0, cosine of 0 is 1. So on the top I get rg times mu s. On the bottom I get 1 minus 0, so I divide by 1. So I actually get the square root of mu sg. I get the same thing when I let theta go to 0. That's cool. Okay, now what about the case where mu s is equal to 0? If that's the case, then this term goes away, and that term goes away, and I have sine over cosine, which is tangent. So I get those other two solutions with this, and that's really kind of cool. Okay, so let's plug it into the calculator and see what happens. So switching over here, back to the computer. So what am I doing here? Let's see. I need theta. I got that. And I'm going to use mu dry. So let's just print, let's do Vmax equals I'm going to type in the equation. Square root r times g times sine theta minus mu dry times cosine theta. And watch your parentheses. There's that one. Divided by parentheses cosine theta. Oh, that one's plus. Cosine theta minus mu dry times sine theta. And let's say print max speed equals Vmax meters per second equals Vmax times 2.24 miles per hour. Let's see what happens. 82. Something's not right. I mean, they go faster than 82 around those curves. I'm pretty happy with my solution, but the numbers just aren't. Maybe I got my radius wrong. What if I make the radius 400? Oh, there's no R in there. No, there is. It didn't change. Oh, RT. RT. I have RT. That's why these are wrong. So no friction, I need the RT. I was using this R up there. That's the maximum speed for that dumb on-ramp. Wow. If you were watching this in the past and you're like, you're back, 10 minutes ago, and you're like, dude, this guy's making so many mistakes. Can't you see the mistake? I see the mistake now, and I'm not going to change it because that's the kind of guy I am. I'm just going to roll with it. So if I just change those two and put this back at 300. Okay, so now I have no friction speed of 100, the max speed of 191. I'm pretty happy with that. Because if you increase the radius a little bit, it gets a lot higher. If you increase the coefficient of friction, it gets higher too. And in fact, those cars are going so fast that there's the normal force can actually be greater with the air drag pushing down on it and giving it a greater normal force. So I'm cool with that. I'm pretty happy. Okay, let's look at. I'm not done. No, I'm not done. We're gonna keep going. The bell doesn't dismiss you. I dismiss you. Okay. So what about the minimum speed that you could go around this track? Because if I go back over to this picture, if this car is going too slow, it would want to slide down. So that would mean this friction force would be this way. And it's not too difficult to change that, right? Because all I need to do is go over here and say, if I change the direction of the friction force, that's going to be positive. It's going to have a positive x component of the friction force, and the y component's also going to be positive. So down here, I can just do the same thing. This is going to be negative. I should get a red pen. I'm not going to. This is negative. And then this one is positive. So this, when I solve for mg, is positive. And this one up here is negative. So this is negative, and that's positive. Negative, positive. Okay, now you can see what happens. That is possible, and I think I know what's going to happen, is that this sine theta minus mu s cosine theta is actually going to be a negative number, and you're going to get an imaginary number, which means you could be stopped and stay there. Okay, but let's just calculate that real quick. Let's just do a quick calculation. I'm just going to print it out. Let's say print sine theta minus mu dry times cosine theta. If this number is negative, then there's no answer. It's negative. Say, so when I take the square root, because the bottom is going to be positive, I take the square root to get an imaginary number. So this means that you could be stopped and you would not slide. What if it's wet? What if it's wet? Let's do that. So I can change that and see, this is why I use Python. I can just change this to wet. And now it's not negative. you would slide down. So now let's calculate V minimum. Let's call it V min, even though this is V min wet. It's going to be the square root of R. It's going to be the same thing. I'm going to copy this. Oh, wait, don't type it. Yes. RTG, this is going to be minus. This is going to be wet. This is going to be plus. And this is going to be wet. Run it. Oh, I didn't print it. Print. Min speed. V min. Meters per second. Equals space. V min times 2.24 miles per hour. Run it. Look, I got all the answers right here. 54. You have to go at least 54 to prevent from sliding down that ramp. And that's that. Okay, so yes, that was a little bit longer than normal, but you get all those problems in there. And you can see two things that I love. Working out the problems analytically, not putting in the numbers, and then putting the numbers in Python, because then it's easy to change things around and play with the numbers and stuff like that. So, like I said, I'm going to save this. Let's save this as car turning road. That doesn't really make sense, but I'm going to give you a link to that. I'll give you a link to my derivation of the centripetal acceleration, and hope you like that.